So in last lecture, we talked about this diamond structure. Okay, this structure is quite important for 3D structure. Let me try to talk about this diamond structure. This diamond structure is two FCC lattice. FCC lattice means face center cubic. Okay, this is cubic. Okay, this is a blue ball. It's just similar to atom at the 8th corner for this. Why this? Okay, so we add 6 red ball. Okay, the 6 atom at a 6 different position at the face center. Okay, so this red ball and plus this blue ball we call FCC lattice. Okay, this is one FCC lattice. So diamond just 2 FCC lattice, and we shift one FCC lattice along the 104, 104, and 104 direction. You can see that here we shift. Sorry, here we shift 104, 104. This we shift 104. This we shift here. This we shift here. Okay, put them together. This is a diamond lattice. Why diamond lattice is important? Because silicon, gallium arsenide, it has this kind of structure. This is the semiconductor materials. So this material it has to have a band gap. Okay. So borrow this idea because electron has electronic band gap. Use this kind of a diamond structure, so we can construct the photonic structure also has a band gap. Okay, this is the basic idea for this kind of structure. Okay, why diamond structure is important? It has a summary. It has 3 features. One, it has a similar. It has a spherical ball Brillouin zone. Okay, it has a quite similar spherical ball Brillouin zone. So I just show this picture. You can see this is a Brillouin zone. This is a Brillouin zone for this FCC or diamond lattice. Okay, so you can see this is FCC lattice similar to a ball. Okay, similar to a sphere. Okay, why sphere is important? As I said, because of Brillouin zone as a blunt plane, the band gap always open up. Okay, because it has standing wave state. The problem is that for 2D or 3D, different direction, I mean a different key, they have a different location of the band gap. They just do not align. So if it has a spherical Brillouin zone region, just I draw this picture. Okay, this can open up a band gap, no matter how small. Okay, this is a band gap. Okay, this region is a band gap. So this is for this diamond structure. Why this is so special? Okay, band gap. Another, this structure has a wing. Okay, it has a connection channel and a plus ball. Okay, you can see this structure. It has a wing. Okay, this is a wing structure. Okay, this is a chemical bond, and it has a ball. Okay, so this is similar to because for 2D we know that for this cylinder structure or this ball structure has a TM band gap. For wing structure, they have TE band gap. So put them together, they have full band gap. Okay, it's similar to 3D. This is the second feature for this structure. Okay, this second feature. The third feature is they have offset in different layer. Okay, offset in different layer. So I just show this picture to you. Why this cannot connect internet? Oh, this is better. You can see this. This is a very good picture. I show this picture to you. Okay, this is a bottom layer. Okay, this is the bottom layer. So you can see they have a 5, 4 at the corner, 1 center. Okay, then I go to the up layer. Okay, this is the center. This is the face center. So I add a 4 atom in here. Okay, you can see. Then finally we add this. Another. Okay, this is diamond structure. You have a different layer has a different position. They have offset. They have offset. Okay, this is the basic idea. You can see different color means different layer. It has a offset. Okay, so they have three nature of this So use this idea, we have the Yamanouchi, they has a 3D band gap. I think the more famous one is UDPI, okay? Because UDPI, you can see that they have offset, okay? First, they have orthogonal each other. Another thing, different layer has offset. So this is quite similar to a diamond, okay? So the first successful 3D band gap, 3D photonic crystal is a diamond structure. This is just ball, but they increase the radius of ball that makes the different ball overlap each other. They provide a continuous wind channel. Okay, they provide a continuous wind channel. This is a diamond structure. This is the first idea. Okay, from a diamond. I think other ideas are quite similar to diamond. They have offset. Okay, they have offset and orthogonal orientation. Okay, then we also have this kind of structure. They use 2D photonic crystal, but they stack the 2D photonic crystal in different layers. Like this column, and this is hole, and column, hole, you can see. But their positions are offset each other. Okay, so they can open up a band gap. This is a very important diamond structure. Because I believe someone who study the semiconductor physics, if you cannot understand the diamond structure, I think you cannot learn the semiconductor physics. Because silicon has this kind of structure. Okay, I think everyone should know this. Okay. Then we talk about this defect. It's quite similar to the 2D and 3D. They certify the variational principle. Okay, when you decrease your permittivity, okay, you remove one column, you decrease your permittivity, you just increase the eigenfrequency. Okay, this is air defect. We call it air defect. Okay, so this is eigenmode show the monopole. Okay, show a monopole shape. Okay. Similarly, when you increase the radius, you increase the permittivity, you just decrease your eigenfrequency. So this band is from called a dielectric band. Okay, it will decrease. You can see the eigenfrequency decrease it from top band. So this is show a dipole shape. This is just similar to 2D. Okay, we also have the line defect. It's also similar to 2D. I just skip this part. Okay, I think the most difficult part is for the surface state. Okay, for the surface state, I also draw this picture for the surface state. A surface state. I draw this picture. First thing, you should identify where is the air line. Where is the air line? Okay. So why the air line has a curve in this part? Okay, this is the important thing. Why is a curve? Because this is the ky component. I just draw this bread zone. We call it 4x m. Okay. Why along? Sorry, this may not be right. Now, x m. Let me take a look what's the name. Okay, gamma mk. So it's gamma m. We call this gamma. This gamma. This is x. This is m. Okay. So along this is x. So you can see here, this is origin point in gamma. Okay. So along the x to m, this line, the ky has a constant. The ky has constant, and the kx will be changed linearly. So this is the reason why it has a curve. Okay. But along the gamma x, the ky equal to the kx equal to 0, ky linear change. This is a totally linear change. So it's a linear. So at this region, this region is a guided mode. Okay. This region is a guided mode. So surface state just below this region, also between the band gap, okay? Also between a band gap, because they are localized at the interface. They must localize at the interface. Okay, this is a truncation layer. They localize the wave to something here, okay? I mean the wave will decay along the photonic crystal because it has a band gap, okay? A wave also decay along air because it has the right-hand side of this air line. It has a guiding mode. So this is we call it surface state. Okay, we call it surface state. Okay. This is a basic idea. Okay. It's similar to the 2D, but I think the difference is how to draw this airline. Okay. Now we talk about the photonic crystal fiber in the last lecture. I think, and the photonic crystal fiber is very important. This is a typical structure. This is just glass with a hole. Okay, glass with a hole. This glass. And air hole. This is air hole. This is air hole. This is glass with air hole. Because this is photonic crystal fiber, so Kz, I mean the propagation vector along this direction should not be equal to 0. It should not be equal to 0 because the wave should be propagation along this photonic crystal fiber. Okay, then we can draw this dispersion relation. Okay, so the region we use is a red region. Why? First thing, Kz, the Kz should be cannot be too large. Okay, because they has a propagation wave along this direction. Another thing, they should be confined because this band gap, it should be confined. So this it should be at this region. The white region is band gap, and this should be up to this in the left hand side of this air line. Okay, if some move around here. If the mode around here, this is the surface state. I mean the wave will constrain at this edge of this fiber is not go. So the mode should concentrate at the center of the defect. This is the basic idea. Okay, so I just show this picture. Okay. So the mode we want is something like this. So I think the EM wave should concentrate at this defect region. Okay, so this is the mode around here. Okay. You can see here, this is the surface state. Okay, so all the EM field are concentrated in air. So this is something around here. Okay, around here, it's similar to surface state. Okay. So we should make this optic fiber work here. But in practical issue, because they have a fabrication error, you can see this is a real world structure. They have a fabrication error. It's not perfect like this. Okay, so we should increase the air of the defect region to increase that. To make this mode can be, okay, this mode can be, they can separate, okay. That means the red mode and the green mode do not couple each other, okay, make this separate significantly, not couple. If the mode will couple each other, they make this optic fiber cannot work, okay. So this is a mode we want, okay, this is the mode we want. Okay. The red, because it has different symmetry, this red color means a symmetry can be coupled to plane wave. They use LED can excite this optical fiber. Okay. This is something we learned in the last lecture. Okay. This is also maybe also important. I think important for some students. You can learn by yourself this part. Okay. This is something we learned. Okay. So we just finished this review. Okay. So here we talk about this temporal couple mode theory. Okay. In this lecture, we talk about the temporal couple mode theory. So in last lecture, we showed this structure. Okay, this is a interesting structure. This is a filter. It's a narrow band filter. That means the EM wave will pass to this structure within a very narrow band. Okay, within a very narrow band. You can see here. Okay, this is a pass band. It's very narrow. Okay, so at off resonance of this cavity, okay, the wave cannot pass at the end or this side. Okay, it just reflected back. Okay, but on resonance region, the EM wave can couple to this cavity, and the cavity can couple to this side. Okay, so this is an on resonance case. This is an off resonance case. Okay, this is a narrow band filter. This is just a recombination of the line effect. Okay, this is a waveguide structure, and a point defect. This is a cavity. They pull them together to make this filter. Okay, so the problem is how to model this problem. Okay. In my lecture, I think that we should know the modeling technique. This is important. All of you cannot know how to design or how to understand this structure. How to model structure? I think the basic theory is a couple mode. It's a temple couple mode theory. Okay, it proposed by the Professor House in MIT. Okay, this is a temple couple mode theory. I think it's straightforward. Okay, so let me to repeat this temple couple mode theory. Okay, then we can go further. I think every student here should understand this theory because this is very easy, not difficult. Oh, this is a cavity. Okay, this is a cavity. This is a waveguide 1. This is a waveguide 2. Okay, I just make this structure. This is waveguide. This is a cavity. This is a waveguide. Okay, so I just draw this cartoon picture. Okay, and we know that it has a coupling. Tau 1, another coupling we call gamma 1. I draw. It has a tau 2. It has gamma 2. Okay. It has outgoing wave as 1 plus. It has incoming wave as 1 minus. Similarly, it has incoming wave as 2 plus. And outgoing wave as 2 minus. Okay, this is a full physical picture. Okay, so the first equation is we consider cavity. dA over dt equal to I omega 0A. I just draw the first term. This first term, it means if I solve this term, what happened? The A should be equal to exp minus omega 0t, right? Everyone to say that it's very easy to say. So I mean the A is a harmonic oscillator, it's a harmonic wave. Okay. This is means A is a cavity, or this is a cavity, okay, this oscillates. But I put more term, this is ideal case. But when we couple, when this cavity coupled to this waveguide, like this. Right. Okay. You can see here. When this cavity coupled to this waveguide, they will decay. Okay. When they couple to this guide, they will decay. The tau 1, tau 2, similar to last time, they capture the coupling. Okay. Sorry, they will decay. It has some decay. Okay. Then also another term. Maybe another right. So I just draw this small picture. This is alpha 1, alpha 2. I use 2. That's 2. Okay. This alpha 1, alpha 2. This is a coupling from waveguide to cavity. Okay, I mean this is maybe similar to alpha 1. It's similar to alpha 2. Okay. Okay. So this is the first equation, first Gaussian equation. So this equation, it means the first term it has a harmonic oscillator, so there's I omega 0 term. When the cavity coupled to waveguide, it will decay. Okay, the engine will decay because there's a couple, and the decay is T1, T2. Okay, it has a coupled waveguide because it's a lifetime similar to that. Also, this waveguide also has a coupling to the cavity. Okay, because it has a incoming wave. So they should be proportional to this incoming wave and okay S1 and S2. Okay, so I plus S1 plus this is okay. So this is the first equation. This is a very cartoon picture. I think it's easy to understand. Okay, this is for cavity. So then I go down. Okay, I go down. How about for the waveguide? Waveguide. The waveguide, the outgoing wave SL1. I mean L equal to 1 or 2. Okay, and this is a simple form. First, this is considered a reflection coefficient as L plus. Okay, this is similar to reflection coefficient, similar concept. Okay, coefficient. Okay, this is the incoming wave. Okay, this is outgoing wave. Wave incoming and wave return back. Okay, incoming and outgoing wave. And plus and gamma over A. Gamma of A. This means coupling from cavity to waveguide. This is coupling from cavity to waveguide. This is coupling from cavity to waveguide. We call gamma A. This is something we draw that. This is another equation, ground equation. There's a many coefficients, but these coefficients are not, independent of each other. Okay, are not independent of each other. Okay, so first we determine gamma 1, gamma 2. We determine gamma 1 and gamma 2. Okay. Okay. First, we assume that the two, they're independent. We assume that they're independent. How about this later? Independent. That means the cavity coupled to the waveguide 1 and this cavity coupled to waveguide 2 with different parameter gamma 1, alpha 1, and gamma 2, alpha 2. That means these two sets or the parameter are independent with each other. Okay, this is called weak coupling, not very strong. Okay? It's a weakly coupling. Okay? Weak. This is important. So first we assume no incoming wave. Okay, we assume that no incoming wave. Okay, if no incoming wave, I mean S1 plus equal to S2 plus equal to 0. I go to the first picture and say no incoming wave. Okay, no incoming wave. Then we assume tau 2 go to infinity. And okay, because this set is uncoupled to waveguide 1, waveguide 2. Sorry. Okay, that means this cavity only coupled to the waveguide 1, does not couple to the waveguide 2. Okay, why I assume that? Because I said they are independent each other. I said they are tau 1 and tau 2, they are independent each other, so we can use this method. I assume tau 2 goes to infinity. Okay. So here you can verify, very simple. This energy, okay, energy change over time just equal to tau 1 over A squared. Okay. So you can see this equation. I go to the first equation. Okay. Tau 2 here, no, tau 2 go to infinity is 0. Okay. I mean, it's not coupled to waveguide 2. And S1 and S2 also 0. It's because no incoming wave. So this term, okay, just these three terms just equal to 0. So only as this term, they introduce decay because this oscillation, okay, this oscillation does not affect energy. Okay, this is decay. Okay, this is A similar to amplitude, So this is energy. Energy, this is tau over 2. Okay, this is energy. Okay, this is tau over 2. Okay. So this is so when it decay, energy, where from this decay? This is important. Okay, when this cavity, you can see the picture, okay, and you know this part, you have no coupling. When the cavity decay, if no incoming wave, this cavity decay, they will decay to S1, right? Because cavity resonance, the liquid wave, the wave goes to S1. Okay, so S1 is the physical origin of this decay. Okay, so cavity decay, then release energy to S1. Okay, right? It's easy to understand. This one I do not consider because they are independent of each other. So this cavity, when they are decay, they couple to the S1 because no outgoing wave. Okay, no outgoing wave. Okay, so equal to S1. And S1, everyone knows that. From this equation, how about this S1? Because it's 0, how about this 1? Okay, gamma of A. So gamma 1 square over A squared. Oh, we get this very good equation. So finally we get gamma 1 equal to 2 over tau 1. Okay. You can see gamma 1 equal to 2 tau 1. Okay. You can get this equation very easily. Okay. So it means that you can see that. So from this equation, okay, this tau 1, this is a decay or this waveguide amplitude. Oh, okay, this is a complex amplitude. It decay. This decay just coupled to this as 1. Okay, so this gamma 1 should be connected with tau 1. Okay. This is basic idea. Similarly, gamma 2 equal to 2 over. Okay. This is similar. Okay. Because I said because two waveguides are independent of each other. Because it's a weakly coupled, not strongly coupled. Okay. Well, this is the first how to determine the gamma 1 and gamma 2. Okay. This is very simple. This is an energy conservation law. It's nothing but energy conservation. Okay, you learn the energy conservation, right? You learn the energy conservation. Okay. I said, okay, so the physical picture is means that if no incoming wave, okay, no incoming wave, and ignore the couple from waveguide 2, it's just this picture, no incoming wave. The cavity, when they are resonance, their decay as a tau 1, their decay will produce S1. Okay, the decay produces S1. Okay, this is a physical picture. And S1, I just use the gamma 1 equal to A. Okay. Because S1 is just use a coupling from a waveguide. Okay. So you can get this equation. Okay. Get this equation. You don't know this?
Why is there no without why is it without the I omega not A term?
Oh, I omega A term this is A square, this is energy. I omega term, this is just channel energy. This is oscillatory. Like, okay. You can verify. Okay. Let me to verify to you if you have seen. Okay. So I can verify to you. This is finally gamma equation becomes something like here. I move slowly because it's important. You can use this model for research because it's very simple. Okay. So now this model similar to that, right? Because tau 2 go to infinity and no incoming wave, right? I can verify to you. You can see why. Then I dA, I go to a conjugate, right? Equal to, I conjugate all, okay? I omega 0 A conjugate plus A conjugate tau 1, right? It's something like this. I do a conjugate, okay? No problem. So dA square over dt equal to A dA conjugate A over dt is unconjugate dA over dt plus A d conjugate dt. Okay. This is just a chance law. Then I put them together. I do this here. Okay, this is good. Larger. Okay, so A conjugate di over dt, we know that is minus I omega 0 A, right? Sorry, this is minus A over tau 1, okay, and plus A I omega 0 A conjugate minus A conjugate tau 1, okay. So you can see here, they cancel, right? They cancel each other.
Yes.
Yes. So finally, just 2A square tau 1. Okay. So this part, when physically this part, this is oscillatory. It means oscillatory, it conserves energy. This is decay. So this is only has this. So this is a physical region. You can verify by yourself. Okay. This is first. This is first. This is the first condition. Another. I move quickly. Another Another just reciprocity theorem. Do this reciprocity theorem, you can verify the beta L equal to -1, okay, and alpha L equal to gamma L. Let me slightly explain to you why beta L equal to 1, -1. Okay. This is interesting. This is very interesting. Okay. So this is cavity. Initially, we said, oh, no incoming wave. This EIEC equal to 0. Okay. When the cavity resonance, they give the outgoing wave. They give this outgoing wave. We call it E out. Okay. We use same notation better. This we call S1 plus. This we call this S1 minus incoming. Okay. Mathematically, we write this. Okay. We know this gamma equation. Okay. Beta L SL plus equal plus is the gamma. We know the gamma now. Gamma now is okay. Gamma is okay 2 tau 1 right over A right. This is the gamma equation. Okay, so this is the first case, case 1. I mean, no outgoing wave, no incoming wave. The cavity, when the cavity coupled to this waveguide, they produce S1 minus. Okay, this S1, SL minus. Okay. This SL minus. So S1 minus equal to beta 1 plus S1 plus I just draw this simple. So because S1 equal to 0, right? So this just okay. This is equal to 0. Okay, there's no incoming wave. This is the first situation. Then second situation, everything return back. Everything return back. Okay, this is important. It's reciprocal. I teach you. When is cavity coupled, no incoming wave, the wave become outgoing, right? You return back. I mean the time reversal or reciprocal. If there's an incoming wave, then I just move this like a movie. I move everything, go back. Okay, this is a coupling from outgoing wave. I move everything. This incoming, like couple the waveguide. No this part, right? Everything can like a movie. I move to the floor. Okay, so what happened? Okay, this become 0. Okay, because this is 0. Because originally it's something like this. Like I go back. So S plus SL1 equal to 0. Okay, SL1 equal to 0, and the beta 1 S plus equal to equal to so outgoing. So it's not good. Become incoming and plus the 2 tau 1 A1. Okay, so you can get this beta L equal to beta 1 equal to -1. Let me replace this. This is a reciprocal theory or time reversal, something, because it's lossless. What's the meaning of that? You can see initially I changed the rule of S1 plus and SL plus. Okay, because I said initially when a cavity couple their outgoing wave, then I move everything back. This is an incoming wave and I couple cavity. No, this part. 0. Okay. So I change the rule. So the 0 it can become here. This is S plus 0. Okay. This is incoming. This is become incoming. Okay. This become incoming. Okay. Because I said I told this is incoming. I capital cavity. this is 0, okay, this is 0. So you can say beta L in no choice to be equal to -1. Okay, this is the reciprocal theory. Okay. Okay. Do you understand this part? Do you understand this part? I just change the rule. Okay, I change the rule here. Initially, no incoming wave, the cavity coupled to this outgoing wave. Here, I make the outgoing wave become incoming wave. They couple a cavity. Know this part. Okay, this part equals to 0. This is a fully reciprocal theory. So beta L equal to -1. Beta L is -1. This is something. Oh, this part is very simple. Alpha L equal to gamma L. I go to the first picture. You can see why. Okay. The alpha L means the coupling from a cavity. This is coupling from waveguide. This is coupling from cavity. They should be reciprocal because there's a mutual coupling. It's also reciprocal theory. I just go through this later. Okay. The alpha 1 means the coupling from waveguide to cavity, and the gamma L is the coupling from cavity to waveguide. So it should be same. Okay. It should be same. So finally, we get this so elegant mathematical equation. Beta L equal to -1, right? Gamma is something like this. Okay. And gamma equal to alpha. Okay. So you can see. They only had 3 unknown, omega 0, resonance frequency, gamma 1, gamma 2. Okay. No other unknown. They have only 3 unknown. So this is easy to fit by your experimental result, okay, or simulation result. Okay. So initially they have how many unknown? You can see. Right? Tau 1, tau 2, 1, 2, 3, 5, 6, 7, 8, 9. They have many unknowns. Then you can reduce them. Okay, that means alpha 1 should be equal to gamma 1, alpha 2 equal to gamma 2. Okay, and the gamma 1 can be connected to the tau 1. Okay, and the beta L equal to -1. Okay, so everything can reduce. So finally, you get this so elegant couple mode theory. Okay, so here was a physical insight. You can see with this couple mode theory. The transmission and the reflection, okay, we can study. First, no input power at right. I assume that no input power at right, okay, no input power. This is a real situation because we come here, okay. If no input power at right, I just draw this equation, okay. Use Fourier transform, I omega is something like no S2 plus, because no wave coming from this side. So this is okay, I draw these 3 equations. And finally, I get the transmission coefficient. Okay, you can get by yourself. Not difficult. You can see this is a physical meaning. 1 omega equal to omega 0, we call Lorentz peak. 1 omega equal to omega 0, and the tau 1 equal to tau 2. What happened? Just equal to 1. Okay, transmission is perfect. If tau 1 equal to tau 2, this is tau over 2 squared. It's a cancelled part, so equal to 1. When tau 1 equal to tau 2, we have a perfect transmission. Okay, this is achieved to single mode because it's a single mode assumption. Emission is symmetric. Okay, symmetric. Symmetric is important. Why tau 1 equal to tau 2 will go here? That means this waveguide settings or configuration should be same with this waveguide, right? So this gamma 1 or this tau 1 equal to tau 2 because this waveguide is same with this is symmetric. Okay, this is symmetric. So they can achieve this perfect transmission because it's symmetrical. It's 2 waveguide. So this is tau 1 over tau 2. Okay, tau 1 equal to tau 2. Okay, I go to this case. I jump to this case. This is an interesting case. Okay, you can see here. This is we call a splitter. This is this is 1 watt and power. They can split 50% to here and 50% to here. Okay, this is a perfect splitter. How to achieve? Okay. Remember the initial condition, we have the 1 channel. I go to the first one. First one, we only have the 1 channel in here. How to achieve the perfect transmission? I mean the tau 1 equal to tau 2, right? Tau 1 equal to tau 2. Here, the difference. Okay, this is the transmission condition. Is 1 over tau 1 equal to 1 over tau 2 plus 1 over tau 3. Okay, because we have 2 channels in here. Okay, satisfy this condition. Okay, so this condition tells you that if we know this additional circle, what happened? Cannot achieve, right? If you notice addition circle, every channel are same, right? If every channel are shared, this condition cannot be satisfied, right? Remember this? You cannot understand. If I remove here, these three channels are same, right? 1, 2, 3, they are same. When they are same, they decay 1 over tau plus 1 over tau. This is tau over 2, right? This is tau over 1. They cannot satisfy, right? So you should add some additional channel, make tau 2, tau 3 different from tau 1. They can make this perfect transmission. This is from model. From this model, we understand this physics. Okay. So this is a key point. Okay. So why this model is important? This is a decay channel. Another thing I want to talk about is resonance absorption and radiation. Resonance absorption and radiation. So this is called as air bridge structure. Okay, this is a cavity. This is a photonic band gap structure. So there's no transmission along this side. I mean, tau 2 go to infinity. Okay, but they will radiate. They can be radiated. So this is the model. Okay, this is the model with waveguide. They couple with waveguide, and they are also radiate. They have also radiation loss. Okay, how to achieve the 100% radiation loss? So everything is same. Everything is same. You can see this is the channel. Okay, originally the channel is waveguide, right? The channel is waveguide. Okay, this is original case. Here, no waveguide because it's a band gap, right? No waveguide. This channel is radiation, all this radiation. So how to achieve tau r equal to tau 1? Also say, okay, I mean the radiation rate it should be equal to this lifetime of tau 1. Okay. So this is 100% radiation. You can achieve 100% radiation. Remember the case. Remember the original case. It's very similar. This is the first case. You can see. This is symmetry. This symmetry. Everything is same. So I can go here, couple to waveguide and couple to here. 100% transmission at the resonance frequency. But here is no waveguide channel, but a radiation channel. I change the radiation channel. Oh, this is radiation channel. Okay, this radiation channel. So this tau 1 also should be equal to tau r to make this 100% radiation. It's quite similar. It's quite similar. Similar, we also can obtain the 100% absorption if radiation loss equal to 0. But we also can choose this condition. Okay. This condition is very similar to your learning the circuit. Your learning the circuit is very similar. This output, this source, this VR source, this R output. How to achieve the maximum power is R equal to Rs, right? You learn this, right? It's similar to that. Okay. These channels will balance each other. Okay. I mean, why this has a 100% radiation. This integer coupled to this waveguide, and a waveguide coupled to this outside. Okay. This transition can be 100%. One is tau r equal to tau 1. Okay. It's tau 1. Okay. There's a lot of other applications. If no waveguide channel, I mean no waveguide channel. Okay, waveguide channel is no waveguide. It only has absorption and radiation. When they are equal to each other, they also can be achieved 100% absorption. It's everything is same. Okay, everything is same. Okay, it's called critical coupling. You can read part by yourself. It's not difficult. It's not difficult. I have no time. I mean, I must finish the one case. This part is easy. Okay, you can learn by yourself. Okay. Think about this. Why this is important. I talk about this last one because this is recently work. This is by the CT chain, HKUST, the professor. The professor, I recently they get a very big project called LE. Okay, it's I mean 1亿港币. How to translate? I mean, it's maybe 100 million. 100 million. They get this project. I think the main work, why the panel give this so big fund is by this work by the photonic crystal. It's published in Nature Material in 4 years ago. Okay? They call it Dirac cone. So everything is easy, not difficult. Okay? But that has a good idea. You can see this is a 2D photonic crystal. Okay, you learn that during the course. This is a TM wave photonic crystal. They just set the radius r equal to 0, point A, and the permittivity with some constant, you'll find it has this point. This point, they have 3 band degenerate at this point. Okay, this is flat. This is flat. It's a monopole mode. This and 2 is a dipole mode. And 3 degenerate at the same point. This point they call it Dirac cone because they has you can see this group velocity equal to 0, and this group velocity is positive. This is negative, and put them together, average is 0. Put them together, average is 0. This is can be achieved called 0 refract index metamaterial. Okay? 0 index. What's the meaning of that? Because this is a case. Then they can realize a length. Okay. This is the case. Okay. You can see this is a wave coming here. They go to a photonic crystal. Okay. This is a circle in here. Everyone know if the face and this curve are same, they will focus on this point, right? The face are same, they focus on this point, no problem. Okay, because this is the same. But if for original problem, if you see a medium, this distance, you can see the distance are different, right? So phase delay should be different, right? Because the distance are different. So it cannot be achieved this same phase here. But why this structure can achieve? Because I said they work, they operate the photonic crystal at this point. At this point, they effectively can be equivalent to a 0 refract index. I mean, n is equal to 0 effectively. If n equal to 0, what happen? How about the velocity? How about the velocity? N equal to 0. C equal to omega over k, right? K, when n equal to 0, k should be equal to 0, right? So C equal to infinity. What's the meaning of that? No phase delay. Right? Very large velocity, so no phase delay. So from here to here, no phase delay. Everything are same phase, so they can focus here. This is a very magic. They do an experiment to verify. This is simulation result. So why they can do a 0 index metamaterial? Because they work at this point. This point, they has a degenerate. Okay, degenerate. They have 2 dipole mode and 1 monopole mode. So I use my code because I ask you to write a code. You can use your code to verify. Okay. Last night I write my code. Okay, I write my code because they has a task 1 for you. You can realize by this. It's easy. This is a gamma point. Okay, this is a gamma point. You can see. This is band 1, band 2, band 3. This is degenerate to this point. This is k to 0 here. This is flat, you can see. This is dipole. I draw this eigenmode. Okay? It's a monopole mode and 2 degenerate dipole mode. So these 3 degenerate to this point. This is group velocity equal to 0. This group velocity is positive. This is negative. So add them together, average 0. Okay. So this is 0 index metamaterial. Okay. This is eigenmode. This is, you can use your program to realize this. So they can to achieve this so magic phenomenon. Okay, they can do this length because there's no phase delay. Even the distance, they have different distance as different. Okay, they publish in the Nature material. They give a very, they publish paper. They give very nice name. They call it accidental degeneracy. What's the meaning of that? It means if you check your material, they cannot degenerate it. They must tune this very carefully. Occasionally, you make this. They call it accidental degeneracy. Okay. And now they call this Dirac cone because it's something like this, like a cone. Okay. They call it Dirac cone. Okay. Okay. So this will give this name. I think this paper is highly cited. I mean, 200 or 300 times. Okay. This is just 2D photonic crystal. Okay. A 2D content, not very difficult. Okay. So, okay. So, thank you. Okay. Maybe next lecture I will repeat some couple more theory because we haven't had time for this.